Hello everyone, welcome to this lecture on Unit 1 Introduction to the Internet of Things. In this session, we will explore the fundamentals, architecture, and applications of IoT. We will be taking a problem solution approach, understanding why this technology exists before diving into how it works. So, why IoT? Before we define the technology, we must understand the core necessity driving it. We need IoT to solve specific problems. First, automation. We need to reduce human interventions in repetitive tasks. Second, efficiency. We need to optimize resources like energy in smart grids. Third, real time monitoring. We need instant visibility into system health, whether that's a factory floor or a human heart. And finally, precision. We need to remove human error from data collection. Defining the Internet of Things. Now that we know why, let's define the what. The Internet of Things is a network of physical objects or things that are embedded with sensors and software to connect and exchange data over the Internet. When we say a thing, we mean any object, from a massive jet engine to a tiny thermostat, that can be assigned an IP address and transfer data over a network. System components, the hardware. An IoT system relies on three main hardware components. First, the sensors. These are the eyes and ears of the system, collecting raw data like temperature or motion. Second, the processors. This is the brain. Microcontrollers like Arduino or ESP32 process that raw data. And third, the actuators. These are the hands. They perform physical actions like switching a relay or turning a motor based on the raw data received. Next, communication models. How do these components talk to each other? We use three primarily communication models. Device to device. This is direct communication, often seen in home automations like Zigbee, where devices talk without a central server. Device to gateway. Here, sensors send data to a local gateways. First, the gateway standardizes the protocol before sending everything to the cloud. And last, device to cloud. This is where devices like smart thermostat connect directly to the internet to upload their data. Now, communication technologies. To facilitate this communication, we have various technologies. For short range, we use familiar standards like Wi-Fi for high bandwidth, Bluetooth for wireless, and Zigbee for mesh networking. And for long range, especially for IoT, we use low power, wide area networks like LoRaWAN WAN or cellular standards like NB-IoT and 5G, which are critical for city-wide or industrial deployments. Now let's zoom out the architecture. Because IoT connects billions of different devices, we cannot just plug them in randomly. We need a standardized layered architecture. This is critical for scalability, security, and ensuring that devices from different manufacturers can work together. Now move to the three-layer architecture. The most fundamental model is the three-layer architecture. At the bottom is the perception layer. This is the physical hardware layer. The sensor and actuators in the middle is the network layer. Its job is simply to transmit the data from the sensors to the processing central. At the top is the application layer. This is what the user interacts with, the smart home app or the industrial dashboard. Now, like three-layer architecture, we have also five-layer architecture. For complex enterprise systems, we extend this to 5 layers. We keep perception and the transport, but we add a processing layer, often called middleware, to handle the massive storage and analysis of data. We also add a business layer on top. This manages the overall system logic business models, and user privacy, ensuring the IoT system actually generates value. Now, let's briefly look at the context of this evaluation. We started with the pre-internet era of telephony. Then came of internet of content, the web, and the internet of services, social media. We are now in the era of IoT or machine-to-machine communication. This shift was enabled by three things: the hardware, the connectivity, and the cloud computing. Now, let's see the real world applications. Mostly in smart cities for traffic and waste management, also in the agriculture for small moisturing, monitoring, and automated irrigation, and most commonly in smart homes, automating our security, lighting, and climate control. Summarize the nature of IoT, we look at four key characteristics. Interconnectivity. Anything can be connected to the infrastructure. Then, things related services, ensuring privacy and consistency between the physical object and its digital twin. Heterogeneity. The system must handle devices from different platforms and networks. And dynamic changes. The system must adapt as device sleeps, wake up, or disconnected. Now let's move to the implementation challenges. However, implementing IoT is difficult. Security is a major risk. Simple devices can be hacked to create botnets like malware. Privacy is a conquer due to the massive scale of data collection. And energy is a physical limit. Powering billions of sensors requires highly efficient batteries or energy harvesting. Looking to the future, we are moving towards AIoT, the congruence of AI and IoT. This is the future of IoT. This involves edge computing, where we process data on the device itself to save time. It enables automation systems like drones, and for you as a student, it offers a massive career scope in embedding engineering and data analysis. And in the conclusion, IoT is transforming both the digital and the physical worlds. Understanding the architectures, we discuss both the 3-layer and the 5-layer models, along with the hardware components, is the foundation for your engineering journey in this field. So, thank you for your attention.